There is an element sitting in the periodic table right now that fooled the entire scientific community for 400 years. And the crazy part is, it did it by just sitting there doing nothing. Not hiding in a lab, not locked away in some classified government facility. Sitting in your medicine cabinet. Sitting above your head in the ceiling of every office, every school, every shopping mall you have ever walked through. Sitting inside the magnets that scan human brains in hospitals. And for 4 centuries, the smartest people on Earth looked directly at it, held it in their hands, melted it, poured it, sold it in pharmacies, and still got the most basic fact about it completely wrong. That fact, by the way, was whether it was even alive or dead, whether it was stable or falling apart. And the answer, when it finally came, was so strange that it did not just change what we thought about this one element. It changed what we thought about matter itself. The element is bismuth, number 83 on the periodic table. And I want to tell you its story, because almost nobody knows it, and the ones who do tend to get a little obsessed. I got obsessed the way most people get obsessed with things, which is by accident. I was reading about something completely unrelated, a piece about the materials inside MRI machines, and a single sentence stopped me cold. It said that the superconducting tapes wound into certain hospital magnets contain bismuth. I remember thinking, wait, bismuth? The pink stomach medicine, that bismuth. And then I pulled on that thread, and I am still pulling on it, because every time I think I have reached the end, there is more. Here is what I mean. Start with the smell of an old pharmacy. That particular dry chemical smell that sits at the back of your throat. Bottles of pale powder lined up on wooden shelves. A pharmacist in the 1600s handing someone a preparation for stomach pain, not knowing what was actually in it at the molecular level, not knowing why it worked, just knowing that it did. That preparation very likely contained a bismuth compound, and it was working for a reason that medicine would not discover for another 300 years. 300 years of doing the right thing for the wrong reason. That is where this story lives. In the gap between what people knew and what was actually true. But to really understand bismuth, you cannot start in a pharmacy. You cannot even start on Earth. You have to start somewhere much further away and much longer ago. You have to start at a limit, a hard ceiling built into the structure of the universe itself, a point beyond which creation simply stops, unless something catastrophic happens first. Because bismuth did not form in a mine. It did not form on Earth at all. It was not here when the planet was young. It arrived, the way all heavy elements arrive, from somewhere much more violent and much more ancient than anything we have a comfortable word for. And the story of how it got here is, honestly, the most dramatic origin story of any substance you have ever touched. Before we get there, though, I want to make sure you understand one thing about bismuth that took me a while to really sit with. This is not a rare element locked away in classified research. You can buy a chunk of it online for a few dollars. You can melt it on your kitchen stove in a regular pot. It is legal, it is non-toxic at normal exposures, and it is sitting in products you probably already own. The distance between this element and your daily life is almost zero. But the distance between this element and the stars it came from is, literally, the largest number you will encounter today. That number is coming. But first, We need to talk about what stars can and cannot build, because that is where this whole thing starts, and it is stranger than most people realize. Friends, if this story is already getting to you the way it got to me, do me a quick favor and subscribe, and leave a like. It genuinely helps more than you might think, and there is a lot more of this to come. So, stars. Nuclear engines. The most powerful sustained energy sources in the known universe, running for billions of years on reactions that fuse lighter atoms into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, neon, silicon, and so on. Heavier and heavier. Each reaction releasing energy, keeping the star burning, keeping gravity from crushing it inward. This works beautifully, for a while. The reactions pay out. The star glows. Everything is in balance, the way a business stays open as long as it earns more than it spends. Millions of years, sometimes billions, the engine runs in the black, and then it hits iron. Iron is not special in any poetic sense. It does not have any particular significance beyond one very specific physical fact. When you try to fuse atoms lighter than iron together, you get energy out. When you try to fuse atoms heavier than iron together, you have to put energy in. Iron is the exact point where the math flips. It is the moment the books stop balancing. The star has been collecting income its entire life, and iron is the bill that cannot be paid. For a star that has been burning for millions of years, the transition from iron accumulating in the core to total structural collapse takes, depending on the size of the star, somewhere between a few hours and about 1 day for the outer layers to feel it. But the core itself, the actual moment of implosion, happens in less than a second. The iron core, which can be roughly the size of Earth, collapses to something roughly the size of a mid-sized city in under a second. The density becomes so extreme that the normal rules of atomic structure simply stop applying. Protons and electrons are pressed together so hard they merge into neutrons. The release of energy in that fraction of a second is, by any measure we have, the most violent single event that can happen to an object in the universe. And in that violence, in that shockwave of liberated neutrons blasting outward through the collapsing stellar material, something extraordinary happens. Atomic nuclei that get caught in that neutron flood start absorbing neutrons one after another so fast that they cannot decay between captures. In a matter of seconds, the universe builds things it cannot build any other way. Gold, platinum, lead, and bismuth. Element 83. Assembled in the final screaming seconds of a dying star, from lighter atoms that had no idea what was coming. But here is where I have to tell you something that confused astrophysicists for decades. Something that did not get resolved until a discovery so unexpected that the scientists who made it were not even using a telescope. They were using something that listens. And what they heard, coming from over 100 million light-years away, changed everything we thought we knew about where the heaviest pieces of the universe actually come from. The neutron flood inside a collapsing star lasts roughly 10 seconds, and in those 10 seconds, the universe builds more variety of heavy matter than in all the billions of years that came before it combined. Let that sit for a moment. 10 seconds. The time it takes you to pour a cup of coffee. And in that window, inside the shockwave of a dying star, atomic nuclei are being assembled that could not exist anywhere else under any other conditions. The process has a name in nuclear physics. Scientists call it the Rapid Neutron Capture Process, or the R process. And for a long time it was mostly a theoretical idea, something that the equations said had to be happening somewhere, but that nobody had directly witnessed in action. The R process works because of timing. In normal conditions, if you add a neutron to an unstable nucleus, that nucleus decays before it can absorb another one. The instability wins. But in the neutron flood of a collapsing stellar core, the density of free neutrons is so extreme that the nucleus captures another one, and then another one, faster than it can fall apart. The instability never gets its turn. The nucleus just keeps growing, heavier and heavier, until the flood ends, and the newly built atoms finally get the chance to settle into whatever stable configuration they can reach. Some of them become gold. Some become platinum. Some become bismuth. Now, here is the part that bothered astrophysicists for a long time. When you calculate how many supernovae have happened across the observable universe over all of cosmic history, and then you calculate how much heavy material each one should produce via the R process, and then you compare that total to how much gold and platinum and bismuth actually exists in the universe, the numbers do not match. There is more heavy material out there than all the supernovae in history could have produced. Not slightly more, significantly more. Enough of a gap that physicists knew something was missing, some other source, some other event capable of running the R process at a scale that a single dying star simply cannot reach. For decades, that missing source was a gap in the model. Everyone knew it was there. Nobody could point to it. And then something happened that nobody predicted would happen the way it did, which brings us to the listening machines buried in the ground and to a signal that traveled for over 100 million years to reach them. I keep coming back to one image when I think about what happened next. Imagine two objects, each one more massive than our entire Sun, compressed into a sphere roughly 20 kilometers across. Spinning around each other, getting closer with every orbit for hundreds of millions of years in complete darkness, in deep space, making no light, making no sound, just gradually, inevitably, falling toward each other across a timeline so long that the dinosaurs rose and went extinct and complex human civilization appeared and grew while these two objects were still circling, still approaching, still a long way from the moment of contact. And then they touched. The collision released more energy in its final fraction of a second than our Sun will produce across its entire 10 billion year lifespan. The gravitational shockwave from that impact, a literal ripple in the fabric of space-time itself, spread outward in all directions at the speed of light. It traveled for over 100 million years. It crossed distances that have no meaningful human equivalent. And then it arrived here, at Earth, and passed through two detector facilities on opposite sides of a continent at almost exactly the same moment, causing each facility's laser measurement system to register a distortion smaller than 1/10,000th the width of a proton. The scientists who built those detectors had been waiting years for exactly this kind of signal. When it came, the data was already streaming before most of the team had processed what they were looking at. Within hours, observatories around the world had turned toward the source location in the sky. They found a glow, a fading fireball in a galaxy over 100 million light-years away. And when they broke that light into its component wavelengths, what they saw in the spectral data stopped people in their tracks. The signature of heavy elements, forming in real time, in quantities that no supernova had ever produced. Gold, platinum, bismuth, being assembled from lighter matter in the neutron flood of two colliding stellar remnants, right there in the data, measurable, real, the largest natural chemistry experiment ever observed by human instruments. The mass of heavy elements produced in that single collision, by the best estimates from the spectral analysis, exceeded the mass of our entire planet several times over. From one event, one collision, lasting seconds. And that was the missing source. Not a dying star, but two already dead ones, locked in a gravitational embrace for longer than Earth has existed, finally meeting, and in the process of their destruction, building the heaviest pieces of the universe in quantities that rewrote the budget. The math finally balanced. The model finally worked. And somewhere in that fireball, new bismuth atoms were being assembled that would eventually drift through space, cool, and wait for the next planetary system to form around them. What happened to those atoms after the fireball faded is a story that takes another 4.5 billion years to tell. And it ends in a mine. The bismuth atoms forged in that ancient collision did not go anywhere fast. That is the thing nobody tells you about cosmic chemistry. It is not dramatic. It is not a journey. It is just waiting, on a timescale that makes the word patience completely meaningless. After the fireball faded, the newly built heavy atoms drifted outward into the surrounding space as part of an expanding cloud of material. No heat anymore, no light. Just cold, dark, diffuse matter moving slowly through the void, mixing with older gas clouds that had been drifting since long before that collision happened. For hundreds of millions of years, nothing happened to those bismuth atoms except distance. They spread. They cooled further. They mixed. And then, in a region of one particular spiral galaxy, that cloud of mixed material began to compress. Gravity, which is patient in a way that nothing else is, started pulling the cloud inward. The center grew denser, then hotter, then dense and hot enough to ignite nuclear fusion, and a new star switched on. Around that star, the remaining material flattened into a spinning disk, and within that disk, smaller clumps began to form. Rock and metal accreting into larger and larger bodies, crashing together, melting, re-solidifying, building planets. One of those planets formed at a distance from the new star where liquid water could exist on its surface. And inside the rock that built that planet, locked into mineral structures alongside lead and copper and tin, were bismuth atoms that had been traveling since before that star existed. They did not do anything special when the planet formed. They just became part of the crust, settled into certain geological formations where the chemistry of molten rock naturally concentrates them, and stayed there. 4.5 billion years. That is how long bismuth sat in the ground before anything on Earth was complicated enough to dig it out. Think about what happened on the surface during that time. The first single-celled life appeared in the oceans, then multicellular life, then creatures with shells, then fish, then plants moving onto land, then insects, then reptiles, then the event that ended most of them, then mammals, then primates, then something that stood upright and eventually learned to make fire. All of that happened while bismuth sat in the rock unchanged, waiting, not particularly interested in any of it. What finally got it out of the ground was silver.
Specifically, the fact that bismuth tends to occur in the same geological formations as silver, and silver was something humans desperately wanted. So when miners in the mountain ranges of Central Europe began cutting tunnels deep into the rock in search of silver veins, they kept encountering a strange metallic substance that came along with it. Heavy, slightly pinkish in the light of a torch, brittle in a way that real silver was not. They did not know what it was. They pulled it out anyway, piled it with the waste rock, occasionally used it for things, and moved on.
The bismuth that had traveled across 100 million light-years and waited in the ground for 4.5 billion years was finally above the surface, and nobody had any idea what to do with it. That gap between having something and understanding what you have is, honestly, one of the most human things in this entire story. And it did not close quickly. Actually, the word quickly does not apply to anything in the history of bismuth, and the more I learned about this element, the more I started to think that was almost intentional. Like the element itself was in no hurry to be understood. Like it had the patience of something that formed before the solar system existed and was not going to rush the process of being recognized just because a few centuries had passed. Because here is what happened after those miners pulled bismuth out of the rock. For roughly 400 years, the people who encountered it, miners, metalworkers, pharmacists, alchemists, physicians, argued constantly about what it actually was. Not because they were careless, not because they were unsophisticated, but because bismuth is genuinely confusing to look at if you do not have the tools to analyze it properly. Hold a piece of bismuth in your hand right now, if you have one, and you will understand the problem immediately. The weight of it is close to lead, that dense, satisfying heaviness that makes you feel like you are holding something serious. The color is silvery, but with a warmth to it, a faint cream or pink undertone that changes slightly depending on the light. It does not look like one thing. It looks like several things at once, like whoever made it could not quite decide. And in an era before chemical analysis, before controlled laboratory experiments, before the concept of a chemical element even existed in its modern form, that ambiguity was enough to cause centuries of genuine confusion. Some people were convinced it was a form of lead that had been altered by the specific minerals around it in the ground. Others thought it was a type of tin. Others grouped it with antimony, which has a similar silvery appearance and some overlapping chemical behaviors. The alchemical tradition, which was the dominant framework for understanding materials in Europe for most of this period, did not help. Alchemists thought of metals as existing on a spectrum of purity, with gold at the top and base metals below it, and bismuth fit awkwardly into that framework because it had properties that seemed to place it in multiple categories simultaneously. Some alchemists described it as a metal that was still becoming something else, still in the process of transforming into lead or silver, as if it were caught halfway through a journey it had not finished. What none of them considered was the possibility that bismuth was not on its way to becoming something else, that it was not unfinished or impure or intermediate, that it was exactly what it was, complete, stable, its own thing entirely, and that the confusion said more about the limits of the framework than about the nature of the metal. That realization, when it finally came, took a very specific kind of person to arrive at it. Someone who worked with the material directly, not in an alchemical tradition built on inherited theory, but with their hands, in mines and furnaces, watching what the metal actually did rather than what the texts said it should do. The man who finally gave bismuth its identity
did not work in a university. He worked in a mine. His name was Thomas Garner, and he spent most of his adult life moving between the silver mining regions of Central Europe as a practical surveyor and physician, one of those rare people in the 16th century who combined academic training with actual hands-on experience in the field. He was not famous in his lifetime beyond the communities he worked in. He was not building a legacy, he was solving problems. And the problem he kept running into over and over again in the mines and smelting operations he visited was that nobody could agree on what to do with the heavy pinkish metal that kept showing up alongside the silver ore. Some smelters threw it out entirely, treating it as contamination. Others mixed it into their lead batches without thinking too much about it. A few had noticed that it behaved differently from lead under heat, that it flowed differently when molten, that it left different residues, but they had no framework to explain why. Garner watched all of this and started keeping careful notes. Not theoretical notes, practical ones. What temperature does it melt at compared to lead? How does it behave when you add it to a smelting batch? What does it do to the texture of the final metal? What happens when you expose it to different acids? Over several years, those notes accumulated into something that had never existed before. A careful, systematic description of bismuth as its own material, with its own properties, its own behavior, its own identity, separate from everything else. He compiled this into a technical document that was circulated among mining engineers and metallurgists, not published as a grand scientific statement, just shared as useful practical information by someone who had done the work. The document described bismuth's low melting point with precision. It described the way the metal expands very slightly when it solidifies, which was unusual and which Garner noted because it had practical implications for casting. It described the brittleness, the characteristic that a heavy metal could be broken cleanly by hand rather than bending. And it described the way bismuth separated cleanly from lead during smelting, rising to the surface of the melt in a way that made it possible, with care, to collect it separately. This was not a discovery in the dramatic sense. Garner did not wake up one morning with an insight. He accumulated observations over years and organized them carefully. But the effect was the same as a discovery, because after his document was in circulation, there was no longer any reasonable excuse for treating bismuth as a variety of lead or tin or anything else. The evidence was right there, specific and reproducible and detailed. And yet here is the part that still fascinates me. Even after Garner's careful documentation circulated through the mining community, the broader scientific and intellectual world took another 2 full centuries to formally accept the conclusion. 200 years of people having access to the evidence and still not quite accepting what it meant. The practical world had moved on. The theoretical world was still arguing about categories. It took a French chemist working in a proper laboratory, running controlled experiments with measured quantities and recorded results, to finally close the debate. He compared bismuth systematically against lead, tin, and antimony, measuring density, melting behavior, reaction with acids, and behavior under heat. The differences were not subtle. They were clear and consistent, and completely impossible to explain if you were still working from the assumption that bismuth was a variant of something else. His published paper essentially said, in the polite language of academic writing, that the question was settled and had been settled by anyone paying attention for quite some time. With that, bismuth became officially recognized as its own element. Not because something new was discovered in that moment, but because the evidence that had been sitting there for 2 centuries finally got the formal acknowledgement it deserved. Practice had beaten theory by so long that the gap was almost embarrassing. But here is what I find genuinely remarkable about this timeline. While the scientific community was still arguing about classification, while the alchemists and academics were debating whether bismuth was a real thing or just an impure version of something else, the people actually working with materials had already figured out something that would turn out to be one of the most important practical discoveries in the history of communication. They had figured out that bismuth could be used to print words. And not just words, ideas, arguments, entire movements. The printing press changed the world, and most people know that. What most people do not know is the specific physical problem that had to be solved to make it work, and what material solved it. Metal type, the small individual letter blocks that printers assembled into pages and pressed onto paper, had to be cast in molds. And when molten metal cools and solidifies inside a mold, almost every metal shrinks slightly as it hardens. The letter comes out a tiny fraction smaller than the mold. The edges are not perfectly sharp. The detail is slightly lost. For decorative metalwork, that imprecision does not matter much, but for a letter block that needs to press a clean impression onto paper thousands of times in a row, it matters enormously. A letter that does not perfectly fill its mold produces a slightly blurred print.
Multiply that across an entire page, and multiply that across thousands of copies, and the cumulative effect on readability is significant. The solution was bismuth. Added to an alloy of tin and lead, bismuth does something that almost no other metal does. It expands when it solidifies. Not dramatically, not enough to crack the mold, but just enough to press outward against every surface and fill every corner perfectly. The letter comes out sharper than the mold, the edges are cleaner, the impression is crisper, and the alloy holds up under the repeated mechanical pressure of the printing press without wearing down too quickly. The early printers who developed this alloy did not know why it worked at the atomic level. They did not have the conceptual tools to ask that question. They just knew that certain proportions of certain metals produced type that printed clearly and lasted well, and they passed that knowledge on through apprenticeships and workshops from printer to printer across generations. Every book that travelled across Europe in those first 2 centuries of printing carried bismuth inside it, in the metal of the type that made the words legible. The arguments that broke apart old institutions and built new ones, the scientific observations that rewired how educated people understood the universe, the translations of ancient texts that connected the present to the distant past, all of it moved through bismuth. An element that nobody could agree on how to classify was quietly carrying the entire project of the modern world forward, one printed page at a time. And while all of that was happening, while bismuth was reshaping how knowledge travelled, something else entirely was happening with it in the courts and private chambers of the wealthy. Something that, depending on how you look at it, was either the first real advance in consumer safety in European history, or just a slightly less harmful version of something genuinely terrible. For roughly 2 centuries, the most fashionable people in Europe were slowly being harmed by their own beauty routines, and not a single one of them knew it. The standard cosmetic for achieving pale, bright skin in aristocratic and wealthy circles was a white paste made from a lead compound mixed with vinegar. It had been used since ancient times. It was considered refined, sophisticated, a marker of status,
The higher your position, the more carefully you maintained that perfect white complexion, and the more of this paste you applied, the more frequently, the more thoroughly. Wealthy women and men in formal court settings would layer it on every morning as a matter of routine, the way someone today applies moisturizer without a second thought. The problem was that lead absorbs through the skin. Slowly, over months and years, it accumulates in the body. And the effects build gradually enough that nobody connects them to the cause. First, a kind of fatigue that comes and goes, then digestive problems. Then something harder to describe, a fogginess, a slowness, tremors in the hands that appear and worsen, teeth loosen. Skin that was once healthy starts to look grey and damaged beneath the paste. So more paste gets applied to cover the damage, which accelerates the damage. It was a perfect and terrible loop, and it ran for generations because nobody understood what was driving it. Into this situation came bismuth oxide, a white powder similar in color and texture to the lead compound, stable enough to apply to skin, and dramatically less toxic at normal exposure levels. It did not absorb through skin the way lead did. It did not accumulate in tissue. You could use it daily and not be slowly harmed by it. By the standards of what it replaced, it was genuinely safe. I want to be honest about what that means. Safe by comparison to something that was quietly causing serious harm is not the same as safe by modern standards. But in the context of the time, switching from lead-based white cosmetics to bismuth oxide was a real improvement in human well-being, even if nobody framed it that way. There was no announcement, no public health campaign, no moment where someone declared the old way dangerous and the new way better. It was a gradual commercial shift, driven partly by availability, partly by the fact that certain apothecaries and cosmetic makers noticed that their bismuth preparations caused fewer of the problems associated with the lead ones. The irony is exquisite. An element that nobody could classify properly, that spent centuries being mistaken for lead, ended up being the thing that partially replaced lead in one of its most harmful applications. Bismuth, the metal that looked like lead, turned out to be the antidote to lead's worst behavior. And the same apothecaries who were selling bismuth oxide as a cosmetic were also selling bismuth compounds as medicine. For stomach pain, for digestive problems, for inflammation of the gut. Not because they had any theory about why it worked, just because patients who took it reported feeling better, and in medicine, that is usually enough to keep something in use. That empirical pattern, bismuth works on stomach problems, we do not know why, but it does, ran for 300 years without anyone seriously questioning the mechanism. 300 years of effective treatment resting on zero theoretical foundation, just observation, repetition, and results. The explanation, when it finally arrived, required first making one of the most disruptive medical discoveries of the 20th century. And that discovery came from two people who were so thoroughly ignored when they first presented their findings that one of them took a step that was almost unthinkable in the medical research community to make anyone pay attention. A pathologist named David Reeves had spent years studying tissue samples from patients with chronic stomach ulcers. Not the kind of ulcers that came and went with stress or diet, but the persistent, recurring ones that kept coming back no matter what treatment the patient received. The conventional wisdom was clear and settled. Ulcers were caused by excess stomach acid, aggravated by stress and lifestyle. You managed them with antacids, you told patients to eat bland food and reduce stress, and you accepted that for most people the condition was chronic and permanent. It would flare up, You would treat it would calm down, and then it would come back. That was just how ulcers worked. Every textbook said so. What Reeves kept seeing in his tissue samples was a pattern that did not fit that explanation. A specific type of spiral-shaped bacterium present in the stomach lining of ulcer patients at a rate that was far too consistent to be coincidence. He brought this observation to a physician colleague, James Whitmore, who became equally convinced that the bacteria were not just present, but causative. That they were not passengers in a damaged stomach, but the actual source of the damage. When they presented this idea at a medical conference, the response was somewhere between polite skepticism and outright dismissal. The stomach was too acidic for bacteria to survive there, everyone knew that. It was a basic fact of gastric physiology. Bacteria could not live in that environment. Therefore, bacteria could not be causing the problem. Therefore, the tissue samples showing bacteria were either contaminated or misread or simply coincidental. The meeting moved on. Whitmore was not deterred. He cultured the bacteria in a lab, confirmed they were alive and real, and then did something that is still discussed in medical history circles because of how far outside normal research behavior it was. He prepared a solution containing the live bacteria and drank it himself to prove that ingesting them caused the stomach inflammation that preceded ulcer formation. Within days, he developed the exact gastric symptoms the theory predicted. He then took a course of treatment that included a bismuth compound, and the symptoms resolved. He biopsied his own stomach lining before and after, confirmed the presence and then the elimination of the bacteria, and wrote it all up. The medical community took years to fully accept the findings even after that, but eventually the evidence accumulated past the point where dismissal was possible. Ulcers, in the vast majority of cases, were a bacterial infection. They could be cured, not just managed. And bismuth, which had been treating stomach problems empirically for 300 years, had been functioning as an antibacterial agent the entire time, hitting the actual cause of the disease centuries before anyone knew the cause existed. 300 years of accidentally doing the right thing. And now that the mechanism was finally understood, bismuth moved from folk remedy status into formal medical protocols, into the official treatment guidelines of major health organizations, into combination therapies used by millions of people worldwide every year. But here is what I keep thinking about. If bismuth worked this effectively as a treatment for 300 years without anyone understanding why, what else has it been doing that we have not figured out yet? Because it turns out the story of what bismuth can do is nowhere near finished. And the next chapter does not take place in a pharmacy or a cosmetic shop. It takes place in a physics laboratory, and what they found there broke one of the most fundamental assumptions in all of chemistry. Bismuth breaks 5 basic rules of how metals are supposed to behave, and every single one of those broken rules turned out to be exactly what someone needed. That is not a coincidence. That is what happens when you spend enough time looking closely at something that everyone else has been dismissing for centuries. The useful things were there the whole time. They were just waiting for someone to stop calling bismuth a failed version of lead and start asking what it actually was. Start with the weight. Pick up a piece of bismuth, and the first thing you notice is that it is heavier than it looks. Noticeably dense. The kind of weight that makes you feel like you are holding something with substance. Its density sits between iron and lead, closer to lead,
And that weight gives it a presence in the hand that feels almost geological, like holding a piece of compressed history. Which, as we have already established, is exactly what you are doing. But then tap it against a hard surface, and something happens that completely contradicts that sense of solidity. It shatters. Not bends, not dents. Shatters cleanly, the way a mineral does, the way glass does, the way nothing that heavy is supposed to. The fracture surface catches light and shows a slightly crystalline texture. The sound of it breaking is sharp and dry, more like ceramic than metal. Every instinct you have about heavy things says they should be tough. Bismuth refuses that instinct completely. This brittleness comes from the structure of its crystals at the atomic level. The bonds between bismuth atoms in its crystal lattice do not allow the kind of slipping and sliding that gives metals like copper and lead their ability to deform without breaking. There is no give in bismuth. When stress is applied, instead of flowing, it fractures. This sounds like a limitation, and in some applications it is. But that same rigid crystal structure is also responsible for some of the most interesting electrical and magnetic behaviors in any known metal. Then there is the melting point. At just under 272 degrees on the Celsius scale, bismuth melts at a temperature low enough to be practically useful in precision engineering while still being perfectly solid under any normal conditions. That combination opens up a whole category of applications that metals with higher melting points simply cannot reach. You can use bismuth in systems where you need something to change state at a very specific, controllable temperature, reliably, repeatedly, without degrading over time. The most striking demonstration of this is the class of alloys you can make by combining bismuth with tin, lead, and a few other low-melting metals in specific proportions. The resulting mixture melts at temperatures that would seem impossible for anything metallic. Some of these alloys become liquid in hot water. Not boiling water, just hot water, the kind that comes out of a tap when you turn it all the way to hot. You can hold a solid piece of one of these alloys in your hand, drop it into a mug of hot water, and watch it soften and flow apart within a minute. It looks wrong. It looks like a trick. It is just chemistry. But the property that most clearly sets bismuth apart from almost everything else in the periodic table is what happens when it goes from liquid to solid. When bismuth cools past its melting point and crystallizes, it expands. It takes up more space as a solid than it did as a liquid. Almost nothing does this. Water does it, which is why ice floats and why pipes burst in winter. A handful of other materials do it under specific conditions. Among metals that are solid at room temperature and that humans regularly work with, bismuth is essentially alone in this behavior. The practical consequence of this expansion is that when you cast bismuth or a bismuth alloy into a mold, the solidifying metal presses outward against every surface it touches. It fills corners that a shrinking metal would pull away from. It captures detail that would otherwise be lost. The final cast object is sharper, cleaner, more precise than the mold itself. This is the property that made bismuth essential to early printing type, as we already covered, but its applications go far beyond that. Now add the electrical behavior, and the picture gets even stranger. Bismuth conducts electricity, but poorly for a metal. Its electrical conductivity is roughly 30 times lower than copper. Put it next to the metals that electrical engineers typically work with, and it looks almost like an insulator by comparison. This sounds purely negative until you realize what low conductivity actually means for measurement.
When a metal conducts poorly, any small change in its electrical behavior is proportionally much more visible. The signal-to-noise ratio improves dramatically. Effects that would be buried in the noise on a good conductor stand out clearly on bismuth. This made bismuth the material of choice for generations of physicists who were trying to measure subtle electromagnetic phenomena, not because it was the most conductive material available, but precisely because it was not. And then there is the magnetic behavior, which is where things get genuinely strange. Bismuth is a diamagnet, meaning it is not attracted to magnets, but repelled by them. Most materials are either drawn toward magnetic fields or simply unaffected. Bismuth pushes back, and it does this more strongly than any other metal. The effect is subtle under normal conditions, just a very slight tendency to be pushed out of regions of strong magnetic field, but under a powerful enough magnet, it becomes visible and measurable. In laboratory settings with the strongest available magnets, small pieces of bismuth can be made to levitate, pushed upward against gravity by the repulsion of the magnetic field below them. I want you to picture that for a moment. A chunk of metal, heavy enough to feel substantial in your hand, floating in mid-air above a magnet, held up by nothing except the interaction between its atomic structure and the magnetic field. No tricks, no strings, just physics that bismuth makes visible because it expresses this property more strongly than anything else available. These 5 properties, the brittleness, the low melting point, the expansion on solidification, the poor conductivity, and the strong diamagnetism, each one looks like a flaw or a limitation until you see what someone did with it. And the full story of what scientists did with these properties spans nearly 2 centuries of physics research, beginning with experiments that were trying to understand something much more fundamental than bismuth itself. In the mid-19th century, a physicist named William Callaway was systematically working through a question that sounds simple, but had profound implications. When you place a metal inside a magnetic field and pass an electrical current through it at the same time, what happens to the resistance? Does the field affect how easily the current flows? And if so, by how much? And does it depend on the field strength? For most metals, the answer was yes. The resistance changes, but the change was so small that measuring it required extraordinary care to distinguish from experimental noise. The effect was real, but barely visible. Callaway tried bismuth almost by accident because he had a sample available and was working through as many metals as he could, and the result stopped him immediately. The change in bismuth was not subtle at all. It was large, clean, and consistent. The magnetic field affected bismuth's electrical resistance at a scale that made measurement straightforward rather than heroic. This made bismuth the primary working material for the study of what physicists now call magnetoresistance. And that work fed directly into discoveries that would eventually become essential to every piece of technology that involves reading magnetic beta, which, in the modern world, means essentially everything that stores or processes information digitally. But Callaway's work was just the beginning. Because when physicists in the early 20th century started applying the new framework of quantum mechanics to the behavior of electrons in metals, bismuth became something even more valuable than a convenient experimental subject. It became a window. Every chemistry textbook printed for most of the 20th century contained a specific fact about bismuth that turned out to be wrong. And nobody caught it for decades because the error was, by any practical measure, invisible. The fact was this: bismuth was listed as the heaviest stable element in existence.
Element 83, the last safe ground before the periodic table crossed into the zone of radioactive decay. Everything beyond bismuth, polonium, radon, radium, uranium and all the rest, was unstable. Those elements fell apart over time, releasing radiation, transforming into lighter elements, counting down toward nothing. But bismuth held. Bismuth was permanent. That was the story. And it was in every reference book, every university course, every scientific database. Settled science. Not even a footnote of uncertainty. The reason nobody questioned it was completely understandable. Testing whether something is radioactive requires detecting the particles it releases when it decays. And if an element decays extremely slowly, it releases those particles extremely rarely, which means your detector might sit next to a sample for years and never catch a single event. Absence of detected decay was treated as evidence of stability, which is a reasonable working assumption right up until the moment it is not. A research team decided to push the boundary of what was detectable. They built detectors sensitive enough to catch events that happened extraordinarily rarely, cooled them to temperatures close to absolute zero to reduce background noise to almost nothing, placed a carefully measured sample of bismuth inside, and waited. The cold inside that detector setup was the kind of cold that has no everyday equivalent. The equipment was housed in a shielded underground facility to block cosmic rays and other background radiation that would otherwise drown out the signal they were looking for. The air in that room smelled of metal and electronics, and the particular sterile dryness that comes from systems kept at extreme conditions. Everything was as quiet and as controlled as it was possible to make it. They waited for weeks. And they caught it. A single bismuth nucleus, releasing an alpha particle, a small cluster of 2 protons and 2 neutrons, and transforming in the process into a different element entirely. The decay was real. Bismuth was radioactive. The textbook was wrong. The number attached to this discovery is one of the most difficult to genuinely process in all of science. The half-life of bismuth, meaning the time it would take for half of any given sample to decay, is approximately 19 million trillion years. Write that out in full, and you get a number with 19 zeros after it. The current age of the universe is roughly 14 billion years. Bismuth's half-life is longer than the age of the universe by a factor of over 1 billion. In the entire 4.5 billion year history of Earth, the fraction of bismuth atoms that have decayed is so small it cannot be measured by any instrument that exists. For every practical purpose on any human timescale or any planetary timescale, bismuth is completely stable. You are in no danger from it. The pill you take for your stomach does not become measurably less effective because of radioactive decay. None of that changes. But the physics changes completely. Because what this discovery actually said was not just about bismuth. It was about the nature of stability itself. If the heaviest element previously considered stable turns out to be decaying, then there is no such thing as a truly stable heavy nucleus. There is only slower and faster. There is only decay that happens on human timescales, and decay that happens on timescales that make the universe look young. The category of permanent had been quietly replaced by the category of not yet finished. I find that genuinely unsettling in the best possible way. The ground under your feet,
The metal in your bones, the iron in your blood, all of it is technically in the process of transformation. Just on a clock that makes our entire existence look like a single tick. Stability was never a property of matter. It was always just a matter of how long you were willing to wait. And bismuth, sitting there in textbooks for generations as the symbol of permanence, turned out to be the thing that proved permanence was an illusion. The most stable heavy element in existence is not actually stable. It is just the slowest. Now hold that thought. Hold the image of bismuth as something that appears completely inert, completely safe, completely unremarkable from the outside, while quietly doing something profound on the inside, at a pace too slow for any instrument to easily catch. Because that exact description applies to something else bismuth was involved in during the second half of the 20th century. Something that had nothing to do with chemistry or medicine or physics labs. Something that happened underwater, in the dark, at speeds that terrified an entire military alliance. Naval engineers working on submarine reactor design in the mid-20th century faced a specific and serious problem. Nuclear reactors generate enormous heat, and that heat has to be transferred away from the reactor core efficiently and reliably, or the whole system fails. The standard solution was water. Water is abundant, it transfers heat well, and the engineering around water-cooled reactors was well understood. But water has limitations. It boils at a relatively low temperature under normal pressure, which puts a ceiling on how hot you can run the reactor, which puts a ceiling on how much power you can extract, which puts a ceiling on how fast the vessel can move. The engineers who designed a particular class of submarines in this era wanted to break that ceiling. They needed a coolant that could carry heat at much higher temperatures than water without boiling, that was dense enough to transfer heat efficiently, and that was chemically compatible with the reactor components. What they settled on was a liquid metal alloy, a mixture of lead and bismuth that remains liquid across a much wider and much higher temperature range than water. The bismuth in the alloy lowered the melting point of the lead significantly, producing a mixture that stayed liquid at temperatures where pure lead would still be solid, and that could operate at temperatures far above anything water-based cooling could handle. The result was a reactor that produced significantly more power in a significantly smaller package than water-cooled designs of comparable size. And that power translated directly into speed. The submarines running these reactors could move underwater faster than most of the tracking systems and defensive weapons that potential adversaries had deployed at the time. Naval intelligence agencies monitoring these vessels reported speeds that created genuine tactical alarm. The vessels were outrunning the tools designed to stop them. The bismuth alloy made this possible. The same element that had been sitting in the medicine cabinet, that had been carrying ink in printing type, that had been confusing alchemists for centuries, was now giving a class of military vessels a speed advantage that kept strategists awake at night. But there was a flaw in this design, a single flaw, and it was not a small one. The flaw was this. If the reactor lost power for any reason, the bismuth alloy coolant would begin to cool down, and at around 124 degrees Celsius, it would stop being a liquid and become a solid. A solid that locked itself inside every pipe, every pump, every channel of the cooling system, like concrete setting inside plumbing. And unlike a blockage you could flush or a valve you could open, solidified metal inside a reactor cooling loop could not be cleared at sea with any equipment a submarine carried. The vessel would be effectively dead in the water until external support arrived. This was not a theoretical risk. It happened.
Several of these submarines experienced coolant freezing events during their operational service, some in circumstances that left crews in extremely serious situations for extended periods before help reached them. The engineering teams knew about the vulnerability from the start and worked on solutions throughout the program. Better insulation around the coolant loops, backup heating systems to keep the alloy liquid during low power states, emergency procedures for restoring flow if temperatures dropped too far. None of these solutions fully eliminated the problem. They managed it, reduced the frequency of failures, but the fundamental physics of the alloy did not change. Below a certain temperature, it solidified, and once it solidified in the wrong place, the consequences were severe. The program ran for roughly 2 decades before being phased out. The submarines were withdrawn from service, the reactors decommissioned, and the engineering teams who had spent careers working on liquid metal-cooled naval reactors moved on to other projects. From the outside, it looked like a dead end. A clever idea that did not quite work, abandoned when the operational costs became too high. But the engineers who had spent years with this technology knew something that the program closure obscured. The concept itself was not wrong. The bismuth alloy coolant worked exactly as predicted thermally. The reactor produced exactly the power the designers wanted. The speed advantage was real and significant. What had defeated the program was not the core physics, but the specific operational context. The fact that a submarine occasionally loses all power in circumstances where you cannot simply plug in a backup heater and wait. Put that same reactor technology in a fixed installation on land, where external power is always available, where you can maintain the coolant temperature during shutdown, where the engineering around the liquid metal loop can be designed without the constraints of fitting everything inside a pressure hull, and the flaw largely disappears. The advantages remain. The Achilles heel becomes manageable, and the potential benefits, a compact reactor that runs hotter and more efficiently than water-cooled designs, that produces less long-lived nuclear waste, that is physically incapable of certain kinds of runaway failure, are significant enough that multiple research programs around the world have been working to develop exactly this technology for civilian power generation. The liquid metal-cooled reactor that failed as a naval weapons platform is being rebuilt as a potential solution to clean energy generation. Bismuth, which gave submarines a speed advantage that terrified military planners, may end up contributing to the power grid that charges your phone. The same physics, the same alloy, the same thermal properties, redirected from one application to another by nothing more than a change in context. That pattern, bismuth doing something remarkable in one setting, and then that same property turning up as useful in a completely different setting decades later, runs through the entire history of this element. And nowhere is that pattern more striking than in what happened when theoretical physicists started asking a question that sounded almost philosophical. What if a material could conduct electricity perfectly on its surface, while blocking it completely inside? Not approximately, not mostly, exactly, perfectly. Inside blocks current entirely. Surface conducts without any loss whatsoever. This sounds like describing a material that cannot exist. Conductors conduct. Insulators insulate. A material that does both simultaneously in different regions of itself, governed not by impurity or physical separation,
but by pure mathematics baked into its atomic structure. That sounds like science fiction written by someone who did not fully think through the physics. But theoretical work published in the mid-2000s described exactly this kind of material, derived from first principles using quantum mechanics and a branch of mathematics called topology. Topology studies properties of shapes that do not change when you deform them continuously, properties that are preserved through stretching and bending, but not through cutting or tearing. The classic example is that a coffee mug and a donut are topologically identical because you can smoothly deform one into the other, but neither can be transformed into a sphere without cutting, because the whole changes everything. When physicists applied topological thinking to the quantum states of electrons in certain materials, they found that some materials have electronic structures where the surface states are topologically protected. The electrons on the surface move in ways that are locked in by the topology of the quantum mechanical wave functions in the bulk material. You cannot scatter those electrons backward at a defect in the crystal without violating the topological constraint, which quantum mechanics does not permit. The electrons simply cannot stop or reverse. They flow around obstacles the way water flows around a stone, not because the obstacle is not there, but because the rules governing their motion leave them no other option. The materials predicted to show this behavior needed one specific ingredient. The interaction between an electron's spin and its orbital motion around the nucleus had to be strong enough to produce the topological protection. And that interaction scales with atomic weight. Heavy atoms produce strong spin-orbit coupling. Light atoms produce weak spin-orbit coupling. If you want a topological insulator, you want heavy atoms. Bismuth is one of the heaviest non-radioactive elements available. Its compounds were therefore among the first candidates that experimental physicists tested when they started looking for real materials to match the theoretical predictions. Research groups at several major universities ran experiments using a technique that fires carefully controlled beams of light at a material surface and measures the energy and direction of the electrons that come out, building up a detailed picture of how those surface electrons are behaving. When they applied this technique to certain bismuth compounds, what they saw matched the theoretical predictions exactly. The surface states were there. They were protected. The material was doing what the theory said it should do. The first confirmed three-dimensional topological insulators were bismuth compounds. Not a coincidence. A direct consequence of where bismuth sits on the periodic table, of how heavy its atoms are, of the same atomic properties that made it useful to physicists studying magnetoresistance 150 years earlier. Bismuth keeps showing up at the frontier because its properties keep being exactly what the frontier needs. And what the frontier needs right now, what researchers are actively working toward using these topological bismuth materials, is something that could change computing more fundamentally than anything since the invention of the transistor. The quantum computers being built today fail constantly. And the reason they fail is embarrassingly simple. They are too sensitive to everything. A quantum computer stores information in quantum bits, which exist in delicate states that can be disrupted by heat, vibration, stray electromagnetic fields, even the faint mechanical pressure of sound waves traveling through the air in the room. Engineers building these systems have to cool them to temperatures colder than outer space, shield them from every possible source of interference, and still watch the quantum states fall apart after fractions of a second. The technical term for this collapse is decoherence, and it is the central unsolved problem in quantum computing. Every major technology company working in this space is fighting the same enemy. The information dissolves before you can finish the calculation. The topological approach using bismuth-based materials offers a fundamentally different strategy for dealing with this problem. Instead of trying to isolate the quantum information from the environment perfectly, which is essentially impossible at any practical scale, topological qubits encode information in a way that is mathematically protected against local disturbances. The information is not stored in one place where a single stray photon can corrupt it. It is distributed across the topology of the quantum state, the same kind of mathematical protection that makes the surface electrons in a topological insulator immune to scattering. To corrupt the information, you would need to change the global topology of the system, not just poke it locally. That is a much harder thing for the environment to do accidentally. The specific particles that make this possible are called Majorana fermions. They were predicted by a theoretical physicist in the late 1930s, and they have one deeply unusual property. A Majorana fermion is its own antiparticle. Most particles have distinct antiparticles. An electron has a positron. A proton has an antiproton. Bring a particle and its antiparticle together, and they annihilate. But a Majorana fermion and its antiparticle are the same thing, which means certain interactions that would destroy ordinary particles simply do not apply to them. In the context of quantum computing, this translates directly into stability. Majorana-based qubits are predicted to hold their quantum state far longer than conventional qubits under realistic operating conditions. Majorana fermions do not exist as free particles in nature, but they can appear as collective excitations inside certain materials, specifically at the boundaries of topological superconductors, which are materials closely related to the topological insulators we have already talked about, and which can be engineered using bismuth compounds as a starting point. Research programs at several major institutions have reported experimental signatures consistent with Majorana fermions in these bismuth-based systems. The results are still being debated, the measurements are extremely difficult, and nobody has built a working topological quantum computer yet. But the direction of the research is clear, and bismuth is at the center of it. I want you to sit with that for a moment. The elements that miners in the 1500s pulled out of the ground alongside silver ore, not knowing what it was, calling it by whatever name seemed closest, is now being used in experiments designed to build computers that could solve problems that would take every conventional computer on Earth millions of years to work through. The distance between those 2 points is not just time. It is the entire history of human understanding of matter, compressed into one element's story. And bismuth's presence in that story is not coincidental or forced. It is there because of what it is at the atomic level, because of properties that were fixed at the moment those atoms were assembled in the collision of 2 dead stars over 100 million light-years away. The heaviness of its atoms, which produces the strong spin-orbit coupling that makes topological states possible, was determined before the solar system existed. Bismuth did not become useful for quantum computing research. It always was. We just took a few billion years to figure out how to use it. But here is the part of bismuth's current story that I find most quietly remarkable. Not because it involves the most advanced physics, but because it involves something you can do yourself at home with a pot and a stove and a piece of metal that costs almost nothing. When you melt bismuth and let it cool slowly, withdrawing the heat gradually and evenly, something happens at the surface of the cooling metal that has nothing to do with any of the applications we have discussed.
The bismuth does not know it is supposed to be in a quantum physics experiment or a submarine reactor or a stomach medication. It just does what its atomic structure compels it to do. And what it does, when given the time and space to do it properly, is build geometry. The crystals that form as bismuth solidifies grow in a pattern governed by the symmetry of its atomic lattice. The edges of each crystal grow faster than the center, so each new layer that forms is smaller than the one below it and positioned at a slight offset. The result is a structure of nested rectangular steps, each one set back from the one below at a precise angle, building upward into something that looks like an architectural model of a ziggurat designed by someone with an obsession for right angles. The geometry is exact, not approximately right-angled, exactly right-angled, because the crystal lattice demands it. Then the oxidation begins. The moment the fresh crystal surface contacts air, oxygen atoms start bonding to the bismuth surface, building a film that is measured in nanometers thick, a few hundred atoms at most. This film is so thin that light waves passing through it interfere with themselves. The wavelength of visible light is right in the range where the film thickness matters, which means that different colors of light are either amplified or cancelled depending on the exact film thickness at each point. Different parts of the crystal surface, which cooled at slightly different rates and therefore built up slightly different oxide film thicknesses, reflect different colors. The result is that a piece of metal that was a silver liquid 60 seconds ago is now a stepped geometric structure covered in a shifting interference pattern of deep blue, violet, gold, copper, green, and back to blue again, all of it in precise geometric sections following the crystal faces, all of it unique because no two cooling events produce exactly the same film thickness distribution across the surface. Every bismuth crystal grown this way is different from every other one. The physics that produces them is entirely deterministic, but the outcomes are as varied as fingerprints. This is the thing about bismuth that I keep coming back to, the thing that connects the cosmic origin story to the quantum physics labs to the crystals you can grow in your own kitchen. The properties that make it beautiful are the same properties that make it scientifically extraordinary. The expansion on solidification that produces those perfect geometric steps is the same property that made it essential to printing type. The heavy atoms that produce the iridescent oxide film are the same heavy atoms that produce the strong spin-orbit coupling that makes topological insulators possible. The low melting point that makes it accessible enough to work with on a kitchen stove is the same low melting point that made it useful in precision alloys for fire suppression systems and submarine reactors. Everything connects. The crystal you grow in an afternoon carries the same physics as the MRI magnet in a hospital, the sprinkler head in the ceiling above you, the quantum computing research happening right now in university labs. Bismuth does not have one story. It has dozens of stories that are all secretly the same story, told through different applications across different centuries, always circling back to the same set of atomic properties that were fixed before the Earth existed. And here is what I think that actually means. Because this story has a moral, and I do not want to bury it. We have a habit of sorting things into categories: useful and not useful, important and not important, worth understanding and not worth the effort. Bismuth spent 4 centuries in the not worth the effort category, mistaken for other things, treated as a byproduct, classified as waste material from silver mining. And while it sat in that category, it was quietly doing more than almost anything else in the not worth the effort pile has ever done.
It was carrying knowledge across Europe in printed type. It was treating bacterial infections 300 years before anyone knew bacteria caused them. It was giving physicists the clearest possible view of quantum effects that would eventually become the foundation of modern electronics. The lesson is not that every overlooked thing is secretly valuable. Most overlooked things are just overlooked. The lesson is that the act of overlooking something does not change what it is. Bismuth was always element 83. It always had those properties. Our categories, our assumptions, our inherited frameworks for deciding what matters, those were the variable, not the element. So here is the question I want to leave you with, and I genuinely want you to think about this. If bismuth, an element that was sitting in pharmacies and printing shops and mine waste piles for centuries before anyone understood what it actually was, turned out to be at the center of quantum computing, space exploration, clean energy research, and some of the most fundamental physics discoveries of the last 50 years, what else is sitting in plain sight right now that we are dismissing because it does not fit our current framework for what matters? Write your answer in the comments. I mean it. Because the history of bismuth suggests that the most important things are often the ones that look the least impressive at first glance. And I want to know what you think we are missing. If this story changed how you see the periodic table or just the world around you, leave a like and subscribe. There are 17 more elements waiting, and every one of them has a story this deep.